right, Jaden.
Hello.
Hello. And Merry Christmas to everyone.
Yes, happy holidays. Today, Kip and I are going to try our very best to calculate how fast Santa has to travel to reach everybody's house during Christmas Eve, I guess, right? Is that kind of the plan?
That is kind of the plan. That's the plan. Yeah, and along with that, tonight we're doing something super cool. We're going to be accepting donations. You can send them to my Venmo account, and all the donations will be going directly to the Utah Food Bank tonight.
Yeah.
Yeah. And we also, so how this is going to work is we've got a timer set up in the corner that you can see there. And so right now we've got 15 minutes to solve this equation or this question that we have before us. Yeah. And so if you give us $1, we get 1 more minute to solve it. So that way you guys are in charge. You're telling us.
Yeah. This could be a pretty short stream if you guys aren't helping us along, you know?
Yeah, exactly. So let's get started.
Should we mention our goal?
Yeah, our goal, Jaden. Go ahead.
So we have a little goal for ourselves. I think it's a reasonable goal for how many viewers we get usually. We want $100 donated to the food bank. I know that's not a ton for some crazy streamers out there, but for us, I think that's a humble goal.
Yeah, I think so too.
Okay.
And on top of that, we've decided that if you guys donate over $20 so a donation of $20 or more, me and Jaden are gonna sing a verse of A Christmas Carol. Okay? So we got that going for us as well. So
yeah.
Alrighty. Kelsey, can you go ahead and start our timer?
Thank you.
Okay, our timer is counting down.
I'll let you start us off, Chip.
Okay. What? We're having technical difficulties. Okay. Alright. So to start off, Jaden, how we're going to approach this problem is we know that the Earth is rotating, right?
Right.
So the Earth is spinning around like this, okay? And if you are Santa Claus in this situation, you just stay in that spot, okay? And as I rotate around, then you're going to stay in the same spot, but you're getting around up and down, and you can make it to every single spot on the Earth, right? Okay. So that makes Santa's job a lot easier having to do that, right? He doesn't have to go around the Earth himself. He just has to stay going up and down, and the Earth will actually rotate.
Do some of the work for him. Okay.
Yeah.
Cool. So how do we do that, Kip?
That's a great question. So for starters, Jaden, I think what we need to figure out is how fast the Earth is spinning. Well, we already know that, but we need to figure out how much time Santa has, right, before we got someone writing us something here.
Oh, we got a $10 donation from Carsey. Thank you very much.
Yeah, thank you, Carsey.
That's amazing. Okay.
Oh, and we've got a comment from Shaylee here that says, I'm going to donate. So thanks, Shaylee, too.
Yeah, thank you. You might be singing.
I know.
Okay.
So, anyways, back to what we were doing here. We're already up to $30, dude. We might have to change our goal.
Should we?
Well, actually, I don't know how much we have. Yeah, I don't know. I assumed 30, but we got at least 10.
Where did 30 go?
Dude, I just hope that people are super charitable out there tonight.
We're already there. Let's make it 1,000.
2,000. Okay. So back to what we're doing here. Now I lost my train of thought, but that's all right. So we need to first write down how fast the Earth is spinning. All right. Okay. And I think we looked that up before, Jaden. What do we got?
At the equator, it is spinning 460 meters per second.
So at the equator, okay, I'm going to draw this beautiful Earth here. Is that good enough?
That looks like an Earth to me. Yeah. Well,
okay. So that's the Earth, and it's rotating away. Okay, and which way is the Earth rotating? Let's see here. This is north. This is south.
So
This is
this way, right?
this is gonna be west then,
Yeah.
and this is east. So let's see here. The sun rises over here, sets over here. So it's gonna be rotating that way.
Yeah.
Okay,
Okay.
and it's rotating at what?
460 meters per second. And that's at the equator.
Okay, so that's at the equator. Oh boy. So let's first figure out, I guess, how. Let's think here, Jane. Where do we want to go from here?
Maybe we should
Shaylee donated $15.
Shaylee, thank you so much for your donation. That's amazing.
Shaylee, you were 5 short of what I was guessing, but that's good.
Hey,
So-
thank you.
Our donation goal is like, where's a quarter? We're already there, dude.
Yes, a quarter. Okay.
Okay.
So
Ooh, we're already up to 8 viewers too, so that's pretty good.
yeah, I'm thinking that we might want to find the circumference at the equator.
That'd be a good idea
'cause
too.
then we can find a little bit more of like the distance that Santa has. Does that
Okay.
make sense?
Yeah, that makes sense. One other thing that we should write down is, remember, if I'm rotating, if I'm the Earth and you're Santa, you have a total of 24 hours,
Right.
to get around the whole thing, or to.
Okay.
So that is
So-
our max time that you're allotted.
Okay,
Right.
Santa has 24 hours to deliver all the presents to everybody.
Yeah.
Okay.
Okay. So yeah, let's figure out the circumference. Okay. Jaden, do you want to explain quickly what circumference is?
So circumference, how I like to think about it, is kind of like the distance around a circle. People often think of like perimeters, like of squares or yards or whatever. If you're trying to build a fence, perimeter, but the circumference is the circle perimeter. So it's the distance around the circle.
Okay.
In our case, it would be around the Earth at the equator.
So, do you know the formula for that, Jaden?
Circumference. I'll write a C equals 2 pi
Dude, you made a smiley face.
r.
Look, can you see that?
Yeah, I do. Okay, so 2 pi r. R stands for the radius. 2 is just being multiplied by the pi and the radius, and pi is the 3.1415.
Some
So-
long
yeah,
constant.
right.
Yeah. Okay.
Okay. So now we need to figure out the radius at the equator, right?
I think we already got that.
We do. Yes.
Yeah, we do.
Okay. The radius is 6,378 kilometers.
Should we throw that into meters? Because our velocity is in
just
meters.
Add 3 zeros, erase the K.
Yeah.
That's why
That's,
metric system is so nice. Is because you can add a couple zeros, make it into meters, or take away a couple zeros, make it into kilometers. And if you're gonna go even smaller, like it's nice. So anyone out there, if you're wondering why we're doing meters per second instead of miles or inches or feet, it's because it's nicer. It's
a lot nicer.
easier to handle, right?
A lot easier.
Okay.
Okay. So do we want to go ahead and convert, like, add numbers in now and get our numbers figured out? Sure. Why not?
We have another donation kit.
We do.
Lori, thank you for the donation. $20. That is amazing. I think we gotta take a break from
Okay.
calculating.
What song do you want to sing?
I don't know. Do you know any like full song?
We just need one verse, dude.
Okay, let's do. I don't know. Jingle Bells is off the top of my head.
All right.
Okay, ready?
1, 2, 3.
Jingle.
No, you still dashing through the snow, dude.
Sorry. Okay. I'll follow your lead.
Okay, 1, 2, 3. Dashing through the snow on a one-horse open sleigh. Over the fields we go, laughing all the way. Ho, 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 bells on the ring, making spirits bright. Oh, lips are right and mouth is wonderful too. Yeah! Jingle bells, jingle all the way.
Thank you for your donation, Laura. You're amazing. Was that
good.
enough? Air fire, right?
Oh yeah, 'cause COVID.
Yeah. Okay.
Stay safe.
So
Okay.
that brings us
Dude, yeah,
in this section. I don't know. We're just kind of filling in the bar.
And how much time are we up to? We're up to...
51:40.
Oh,
Wow, we got so much time.
Let's slow down.
Yeah.
Just no. Okay. There's a lot to still do. Right. We haven't gotten too far yet. So where were we, kept?
Dude, we were trying to find the circumference.
Oh yes. Okay. So we have a radius 2 times that times pi.
Yeah, should we just leave this like this for now? Or how do we want to... I honestly, I feel, Jaden, like we need to stick in measurements of radians and keep everything to degrees and radians first instead of...
Okay.
And then I think at the end we'll have to convert
to
back.
Okay.
That's kind of what I'm feeling. So we could get the angular velocity because so one of our big issues that we're gonna have, right, is this was at the equator. This velocity here is at the equator.
Yeah, and
as you travel up
to the poles,
that changes.
You're gonna be going slower, right?
Exactly.
Okay.
But we can actually calculate what revolutions per minute or revolutions per second or whatever we want. And that's really easy to calculate from
because we
24
have our
hours,
period, right? Okay.
And so from there, it doesn't matter at this point up here, that angular velocity is going to be the same as at the equator, right?
I gotcha. That will make it a nice. Yeah, that will be.
Do you think that's
I think
helpful?
you're onto something. Yeah.
Okay. So we have 24 hours for one revolution. That's 24 hours per rev. Okay.
Okay.
So should we go into revolutions per minute? Do we want to get all the way to seconds? Where do we want to get this to?
Maybe per hour because of time zone. Do you think that would work?
Sure.
Or
Let's go with
I don't
that.
know. What were you thinking?
I don't know. Well, I'm just thinking out loud here, Jaden. I don't know if you're catching my drift here, but we'll do 24 divided by 60. Okay, so that's 60 minutes, right?
Yeah.
And this is hours. Rev. Wait. What? Oh wait. No. Okay, then we got. Hold on. 60 minutes and. Wait.
We have another donation. Tristan, thank you. I agree, our song was beautiful.
Dude, our donation goal is, I think we're halfway. Did we make it halfway? Are we above half? I think
we had 10, 20, 10, 15.
Dude, we can do math.
We're
We're at 55!
We're over halfway, thank you. And it's,
Thanks.
We're not even halfway done with the stream. That's wonderful. Thank you.
We might have to bump up our... Dude, I told you we need to bump up our total here.
Hey, I told everyone it was humble goal. Right? If they want to donate more, they can, and we'll be thankful, and the food bank will also be thankful.
Yeah.
Right?
Since Tristan liked the song, should we sing another song?
I don't want to. I want to do math. Okay. 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 Well, thank you. Thank you. Everyone, thank you for your donations. Also, if you have any questions in the chat, if you're like, how come you're talking about radians or what are radians, let us know, right? Just let us know in the chat, okay? Alright, let's continue.
Okay. So we're at 24 hours per revolution. We want to get to revolution. Oh, wait. Per one revolution. So, where's my math going wrong here, Jaden? Help me out.
What's your end goal?
I want to get to revolutions per minute. Because it should be less revolutions per minute. Alright, so this is 24 hours per revolution. Oh, we got to flip this. Wait.
Yeah, so if you just start at one revolution.
Yeah, it's 1 over 24.
Yeah.
That's where I went wrong.
There you go.
Okay.
Okay.
So
That's
then we leave it
so
as 1
we have a question in the chat.
Yeah.
What is a radian? From Kelsey, and why do we like them? So how Kip was saying earlier, if we're using this speed of the Earth, 460 meters per second, that is only at the equator. So what radians and revolutions will do for us is the Earth is all spinning, so that will be constant throughout the whole Earth instead of a changing velocity from the equator to poles. Right? Does that kind of answer the question?
I mean, yeah, to go with it, just to keep it, a radian is it's a measurement it's a measurement of rotation. I'm not sure if you said that like that.
Okay,
but
yeah.
It's a measurement of rotation, or, you hear degrees a lot, but it's similar to degrees, but it's just a different scale than degrees is, but it means the same thing. So, like 360 degrees is 2 pi radians, right? So if you spin all the way around, that's 2 pi radians.
So it's like another different conversion you can do. So if you're talking angles to radians, right, you could do 360 degrees to 2 pi. That's the equivalent radians. It's kind of like converting from feet to meters, right? You have that little conversion. It's just a little easier way to calculate because we're doing the angular velocity.
Exactly.
Right?
So we got a question here from Lori asking, will Santa need to stop for fuel? My answer is no, because I don't think reindeer need fuel.
No, reindeer are amazing, magical creatures. They get all their carrots and nutrients on the go, right? So
right. Yeah.
Santa's magic, it's wonderful.
Santa's got enough food to last 24 hours. For both him and the reindeer.
Yes.
But thanks for that question. That's a great question. So we got, alright. So we have 1 rev, 24 hours. And then from there, let's see here. So then we go to
60 minutes in an hour.
Yeah.
Right, because we're just getting minutes.
So 1 hour, 60 minutes. Like that, our hours cancel, and we get 1 revolution, or, yeah.
1 revolution every...
that's 1, 4, 4, right? Is that right? Yeah.
No,
1,000.
we're missing...
Right?
Yeah.
Jaden, that's right. Look. 6 times 4 is 24. 6 times 6 is 12.
Good job.
Dude, am I right?
Yeah, I like your math. My brain's not working with simple
You're getting ready
core functions, you know?
You're getting ready for the bigger stuff coming up.
Yeah, we'll say that. We'll say that. It's wonderful. Okay. Whew.
Woo!
We got it.
We just had our technician here, our technology specialist, do the math on the calculator, and it's right. So we're good.
Good job, Kip.
Okay.
I believe in you. That's why I said yeah.
Yeah. So we could flip this now, right? So in
1,440 minutes
Or we could figure out how much of a revolution we do in 1 minute by dividing by that, right? So we could do 1 divided by 440. And what this is going to give us, for all you people out there that may not know, if you've ever heard on the planet, you have, your longitude and latitude, and then when you get to smaller numbers, you get to things that are called minutes and seconds. And I'm pretty sure that this is where that comes from. It's how much of the Earth rotates
in 1 minute. Okay, cool.
But I don't know if we need to go that far. Maybe we don't need to. I think we need to get longitude and latitudes figured out at some point here.
Okay.
Or do we want to figure out how much of the Earth he's got to travel in 1 minute here? Or what do we want to? Where do we want to go?
Yeah, that's a good question.
So what we're thinking is, okay, let's think about this out loud for a minute. All right. So he's got 24 hours to go the whole way around. Right. Do we want to block him down? So he's gonna have. If we take this chunk here, right. And he's got to go up and down every little section of this chunk, right? How much of that chunk do we want him to go up and down? And that's the question we got to answer. We got to decide this. This is something that's going to be important for us.
I mean, obviously we want him to get to every house.
Right.
But also there's large bodies of water on the Earth that he doesn't actually have to go to.
Right.
So we're having trouble here. We're trying to think, like, how rough of an estimate do we want to do, or how much math do we need to do, right? That's kind of...
This is a hard problem because the Earth is not, very evenly distributed.
And there's different population densities across the whole Earth.
Right.
So that's something that we also have to think about. The good news is, Kip, we have 51 minutes. So
let's just take a break.
We'll
We'll go get a drink and come back here.
No.
We got do an average.
Okay.
I'll see.
So that would mean, like you said, we'd cover the whole Earth. I think that way. That would be the easiest, because then we wouldn't have to cookie cut our way around Earth or oceans. You think that?
I think that would be helpful, and I think if we took an average, or we made a linear function, okay? Because we know that there are more people that live around the equator than live at the poles, right?
Right.
So we can just throw out a number out there. I don't know what it is. I'm guessing it's going to be like 1.2x or something like that. What do you think? Do you think that's a pretty good...
It might be more than that.
Well, that depends on what our x is, I guess.
Yeah, but I'm thinking, right, Antarctica...
0.
That's pretty much 0, right? Unless there's scientists working over Christmas, and unless we want to count the penguins.
Yeah.
Right?
I want to count the penguins.
But then we'll have regions... do you remember what those are called? The regions outside the equator.
There's like the cancers.
Yeah, and the tropic.
Yeah,
right?
Tropic regions.
So those different regions are going to be dense also, right? So we're going to have this middle section of the globe that will extend past the equator.
Do you think it's going to be exponential?
I think
1.1 to the x.
I don't know about that. I think that would be... I think that looks to me like too much.
km.
What is km?
Kilometers. Our x is in kilometers.
Oh, okay. Sure.
Is that radius from the center, or are we going to go circumference?
Okay. Kip, you know what I am learning today?
What?
This is a lot harder than we originally thought it was going to be, okay?
Okay, let's simplify it then. We're not gonna have a linear. We're just gonna go with an average
Okay.
over the planet, and then once we figure that out, we can come back.
Then we can piece together. Yeah. Okay.
Does that work?
That sounds good.
Okay. And I'm thinking we maybe get rid of numbers first. I don't like working with numbers. I'm a physicist. I don't like working with numbers
That's
until we have to. And we might get some massive nasty equation up on this board, but I'd rather do that than be plugging in numbers.
Let's do that.
Okay.
Okay.
Anyone got a problem with that?
Yeah, let us know. Okay.
If you got a problem, too bad. However, our donations have been slowing down, so they're not liking our content as much. Because Jaden didn't want to sing the song.
Probably. Okay.
Okay.
So what are we erasing here?
All of it.
Really? Okay.
Okay.
But I really like your globe.
Well, we're leaving the globe. The globe is staying. That's a must stay.
Okay.
Erasers
right there.
No, let's. Here we go. Hold on. Okay, we'll leave that. That's an important thing, even though
we can leave the
24 hours is important. But let's first decide. All right, we need this. Okay.
Okay. Yes.
So that's the circumference. All right.
At the equator.
At the equator. Question.
Yes.
Is Santa Claus gonna do this? Is he gonna go all the way up and around the backside? No, he's not, right? Because he's staying in the same spot.
Yeah, we don't want him to do that because then he would not be at nighttime and the kids would see him.
Okay, so that's bad.
Okay, we don't want him to go.
That's bad.
No good.
So he's gonna go up and down.
Yeah.
Right.
Boop, 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 boop.
Okay. So here we have. We don't care about the circumference going this way, right? We only care about half of the circumference. So we want c divided by 2.
Okay. Ooh, that looks nice.
Yeah. So this equals pi r. Okay.
Okay.
So that's good. We're going in the right direction.
We are.
Okay. So now, here's the deal. Oh, dude, we're up to 13 viewers. Should we take a break because we have so many people watching us?
Yeah. Let's take a break so they leave.
Yeah. Okay, so the next thing we have to do here, I'm going to erase this up and down here because this is something really important, all right?
Okay.
So as Santa Claus is moving, right, the Earth is rotating. So as he's coming up, right, the Earth is rotating this way. So he's actually going to, as he gets to the top, he's going to have made this triangle, this line at that, right?
And that would be a little bit exaggerated because we're thinking he's got to be traveling pretty fast.
Right. But we can, we could calculate what this distance is, right? Okay. So whatever his velocity is that he's traveling, v, right? He's traveling at a velocity v. The distance he's going to travel in that time is going to be this, right? And you remember from our equations that we've done before where rate times time equals distance.
Right.
Okay. So we're going to call this VS for Santa.
Okay.
Okay.
VS.
And rate times time equals distance. So if we're trying to find our time, how far he's going to have to travel in that time.
Yeah.
It's going to be distance, right? Or this c divided by 2, right?
Okay.
Divided by v of Santa, okay? And that's going to equal the time it takes for him to do 1 up. Or
1 up?
Yeah.
Okay.
And so from there, okay.
Okay. And this,
we're getting there?
So let's talk about our unknowns, right?
Okay.
So we do not know.
This is the thing we're solving for.
This is our end goal here. So VS, velocity of Santa. That is our goal. Okay. And we're trying to figure out this.
Right.
Right. We know this. We need to figure out this. And then we can figure out this.
Right.
So what else do we need, Kip? I think we need something else.
No, we're getting there. So then what I'm saying is from this time, Jaden,
yeah,
we can. Another thing we do know is the speed of the Earth, right? And we'll call that VE. Okay. And again, if we're trying to figure out this displacement, right, this x here,
Right.
we know the time. We know how fast he's going up, or so we know the time. The time is the big important thing. That's what I always tell all my physics students.
Yeah.
Time is the key when you're working with two different axes, right?
Okay.
So in this case,
that's when we can connect them, right? Because
Right.
the time will be the same for both going up
Exactly.
and down and left, fiddle, right, and
right.
all those words that I just said.
So if we do VE times time, this equals that x distance, right?
Okay.
Okay. So then from there we can replace that t and make it the c over 2 divided by vs times ve equals x. Alright?
Okay. So I just want to clarify what you just did here. Right.
Okay.
So you're saying t is equal to x divided by VE. Okay, this t, right? Because these are
Right.
going to be the same.
Right.
Okay. Then you're like, okay, I'm going to substitute all this into this equation. Then I'm going to multiply by VE, cancel it out, and now it's on this side.
Or what I did is this equals t, right?
Right.
And so I just plugged all this
Into the t.
into
Okay.
the t.
So either way. Okay.
Either way, it's the same thing. That's, they work the same.
Right.
Math makes you do things differently.
Okay,
And it comes out the
I
same.
like
That's
it.
math magical,
I like
by
it. I
the
like
way.
it, I like
Anyone
it.
that was wondering?
Yeah.
Okay. So Jaden, we've got this. All right. So we have now how far he's gonna drift, right?
Okay.
In a certain amount, I guess in a certain amount of time, right? We know how far he's gonna drift. Okay. By the time he gets to the top. Alright? So, if he's drifting like this, we have a problem. He's missing all these houses over here.
And he's missing those houses.
So he has to counteract this drift to stay
Straight up and down.
straight up and down.
Okay. So, Kip, this is still a wonderful math equation, and we're still having so much fun, and we love it.
we are.
Okay, how are we going to counteract this? Right, we obviously know he has to be angled slightly.
I'm gonna throw a y in here. Because we're gonna need a y and x component of this.
Okay, so
So
the
for
y,
what I just
yeah.
did, why I threw a y in here, is because this is the velocity of him traveling straight up and down, which I'm calling his y velocity. Okay.
Right.
But to counteract this, his drifting across the planet,
Right.
he's gonna have to have
A horizontal direction.
Right.
So we're having a vertical direction, and we also need the horizontal to counteract the drift from the rotation of the Earth. Right?
Right.
Okay. Whew.
Okay.
So let's get on the x direction. Let me write this down so we don't lose
Yeah.
track of it.
Agreed.
Okay, so we have c, which is circumference, divided by 2, divided by the velocity of Santa. Cool guy. Okay, and this is going to be all multiplied by the velocity of the Earth. We know that. And that equals our x, which x is the displacement that he, I guess, moves, or I guess as the Earth moves. That's the... Okay, got it.
Okay.
Whew. Now let's figure out the x.
I don't think it's gonna be as bad. I think
Yeah.
it's gonna be better.
Yeah,
Maybe. We'll see here.
we're on to something.
I think we're moving in the right direction.
Yes.
Okay.
Okay. Whew.
Okay. So, do you want me to keep going?
Yeah, keep going.
Okay.
You are the physics man, and this is more physics right now.
Okay, so we know what our display. Remember, we have our displacement x times time, right?
Yes.
Okay. And so we need again displacement is equal to v times time, right?
Yeah.
And so
And is that v e, right?
no, this is just
Oh, are you
Yeah.
just doing a general
so.
equation?
But this, yeah, we'll leave this v times t. So
Okay.
this actually, now that I'm seeing this,
We
I got a
got
sock thrown at me because I'm not
it.
good enough, I guess.
Okay.
So Jaden, actually, this
Yeah.
answers our question for us really easily.
Okay.
If Santa's drifting this way,
Yeah.
right, because of
Yeah.
the Earth,
Yeah.
then he's gonna have to drift back at the same speed.
Oh, okay.
Okay, do you see what I'm saying?
Yeah, I gotcha.
So, right?
So he just has to add a velocity component of the Earth in the opposite direction.
Exactly.
Okay.
So Santa needs to have this is vector components, okay? So we have v of Santa is equal to, in the x direction we're going to say negative VE, right?
Right.
And in the y direction we're going to say VS. Okay?
Okay.
Is that good?
Yeah, that looks great.
So we can
So
find
then
them.
he's just gonna go up and down on the Earth.
Right. Should we show them how to find the magnitude of this? What his actual speed is going to be? Because this right now is a vector, right?
So, do we need to explain what a vector is, or?
I think Jaden should explain what a vector is.
Okay, so with our velocity, right? If you are talking about real life, there's multiple directions, right? In our situation here, we're dealing with two different dimensions, so a y component and an x component. So vertical up and down, and horizontal left and right. Okay, so a vector tells us the velocity in those two directions at the same time.
Alright.
Okay, so we have our x component and our y component.
Okay.
Anything else we need to add?
No, I mean just real
then-
simple. Vectors are just, it has a magnitude, right?
Right.
And a direction associated with it. So I was actually talking to Kelsey about this the other day, and how, so for example, particularly with this speed versus velocity, a speed would say be 30 miles an hour,
Right.
but a vector would be 30 miles an hour to the east or to the west.
Right. North,
right?
west,
Yeah,
east. Okay.
It has a direction associated with it.
Yeah, I like it.
Okay.
Okay.
So to find the magnitude, we take the square root, okay,
Right.
of the and we add them together. So you have this negative VE and you square it plus the y component VS squared, and this is going to equal. And this, sorry, we needed to put this y.
Yeah,
And so this equals VS.
and this
okay?
is the magnitude. So
That
this
is the magnitude.
this is going to tell us how fast he's going. We don't care the direction.
Right.
Right. This one we care about the direction because there's an x and a y component.
Right. I'm already looking at this, Jaden, and it's going to be solid, man.
the spot right here.
No, look at this, dude. He's got to be going
Oh
the
yeah,
opposite
he's
of the
gonna
speed of
be-
the Earth. He's
Well, we know that Santa is amazing, and those reindeer are amazing creatures. They're gonna be going fast. Just a little side note. So there's something called like special relativity, general relativity, and that is when. Well, it matters when speeds are about 0.1 times the speed of light. Okay, so if at the end of this, and we find something that is 0.1 times the speed of light or greater, don't even care about what we just talked about because we would need it. Different equations, right?
Yeah.
But
So
we're still having fun.
we're gonna keep going here. Okay. All right. So we've got this now. Let's write that down and keep that for later.
Okay.
But I think we're on the right track now. So now let's think conceptually for a second here. All right. So the problem is, Jaden. Now this is where things get tricky. All right. So he came. If we think of Santa, right?
Right.
He's coming up, but if he's counterbalancing this, if you're Santa Claus and I'm rotating, right?
Right.
And you're trying to keep with my shoulder, you're gonna have to rotate with me.
Yeah, I'm going.
And so now we got to think about this conceptually here. So now he's got to move over when he gets up to the top, and then he's got to come back down and do that over and over again. But he's got to make sure that he's going fast enough that he has enough time to do that. So I think what we need to think now is he's got 24 hours, right?
Right.
But he actually has, I think, more than that.
Because he'll be going...
Because there's a certain amount of nighttime that exists during those 24 hours, right?
Right.
You'd have exactly 24 hours if he...
If he could stop time and just...
Well, no, he'd have exactly 24 hours if he had only like a split second, right? And,
right.
But he has, let's say, average person goes to bed at 10 and wakes up at like, 6? Should we say 10 to 6? That's not what time I go to bed.
Yeah, sure, I don't know.
But we've got 8 hours, right?
8 hours of nighttime.
Of nighttime.
Okay.
So essentially, I feel like we could say that he has a total of...
But during the winter,
hours.
It's more like...
But people still go to bed, right? Santa's showing up when people are asleep.
Okay, I gotcha.
Right? So he does have this 32-hour window, I feel. Do you agree with me on that?
No, that's a good estimate on how... Because... So, he has this extra time because he is counteracting the rotation of the Earth, right? So he's going with the Earth, and nighttime for each area of the Earth is about, we're saying, 8 hours. So that's
right.
Just
so
an estimate.
A way to think about it is that if you've ever been on a super long plane ride before, and you're going, like, for example, a few summers ago, I flew to France, right?
Okay.
And the sun kind of essentially never set on us. Why? Because we were going...
You're going...
with it, right? The same thing if you're taking a flight from the East Coast to the West Coast during sunset, you can actually, you get like a 2-hour long sunset because you're going with it that way.
Right.
And so you get a much longer time frame.
I gotcha.
Or just on top of that, you also, I guess, you have 8 hours of dark, or you have 8 hours that people are asleep. So for every chunk that he has going up and down, he technically has 8 hours, right, in that chunk of space.
I'm getting it, yeah.
But the problem is by the time he doesn't have exactly 8 hours because he has 8 hours here, but then the sun will almost be rising over here, right?
Right.
So this is these weird kind of questions that you get into where people are like, I left to go to Japan and I got there a day later or a day earlier or whatever it is, and you're like, how did I time travel? Well, you didn't, but it has to do with the rotation of the Earth.
Different time zones on the Earth, so it's like if you're traveling to Japan, we're going to be a totally different time zone. The flight's going to take a certain amount of time. Okay, that makes sense.
Okay.
Okay.
We got a $10 donation from Angie.
Hey, thank you,
Angie, very much. Thanks. We were getting a little short on time there. I was getting worried, dude. Not gonna lie.
We were getting short on time?
I think we're down to like a half hour or something.
Okay, well, this is...
And I don't know if we're gonna get it done at that time.
Well, hopefully we do. Okay, so I think that makes sense. I kind of answered the question, why the 32 hours, right?
Right. Okay, so
Now what?
but we don't
What do we need?
we don't remember we were staying away from hours. But that
Yeah.
that was just to help me conceptualize to
Okay.
think about this. So remember what we're trying to figure out is Jaden, we got this, dude. You gotta stay focused, man. Stay focused.
I would like. Do we need parentheses right here?
Yeah, that would be a good thing because if you didn't, you'd be in trouble.
Yeah, I was thinking we might get some complex numbers. We don't need to deal with those right now.
No, we don't.
Okay.
We might. We might get some error. Okay, so let's think here. So if he's traveling with the Earth this way, all right. So he's gone back now the same distance x, all right.
Okay.
Okay, so
Okay. Keep going.
you thinking this through with me here?
Yeah.
Okay, so then he's got it. So he's up here now, right? He started here, and now he's up back over here essentially because he's going with the Earth. Okay. So now he's got to come back down, and should we could. Dude, this is gonna be rough.
This is gonna be right. That's what we signed up for, Kip.
I know. Let's say that. So I'm gonna just write over here so we can remember. We're gonna say big T like this is equal to that 32 hours we came up with. So that's gonna be our total time that he has.
Okay.
Right? Okay. So this magnitude that we
Do
came
we
up
need
with.
this?
No,
Because we wrote it up there, right?
So this magnitude that we wrote, this
Yeah.
VS, the whole distance that he's gonna have to travel in both. We're gonna have to calculate some surface area, I think, here. Because the whole distance that he's gonna have to travel
it's
is
gonna-
essentially be the
it's-
whole globe, right? I mean, we could
It's-
cut like off this and this if we wanted to.
But that might just make it
Yeah.
more difficult for us.
But
'Cause
he's
of
gonna have to
the-
travel every inch of this globe, essentially.
Yeah.
Right? So
Doesn't want to forget anyone. Doesn't want to forget the people on the boats and
No.
the Eskimos
Yeah.
and the polar bears and.
exactly. Okay. So what we need to do from there. Oh boy.
So we.
What I'm thinking is we need an equation for this t total to figure out how much time he has and relate that to his velocity. How do you feel about that?
Yeah.
Right? Because he's got to travel this whole globe.
Yeah. So I
So
look up surface area of sphere.
I think it's 4. Oh, that's volume.
Yeah.
It's,
I can just
yeah,
look it up.
I think it's like 4 pi r. There's some weird.
Let me.
It's something like that. I know. Where'd that eraser go? Hiya!
Oh, look at this.
What is it?
But it's in miles, dude.
Dude, I don't. I just want to know the
Equation, I know, but it just like popped up on my phone.
Anyways, I'll write this out for now. I'll say that surface area of the Earth, okay, is going to be equal.
We have a comment here.
Yeah.
You need to find an approximation of the number of houses he has to visit.
That'll probably come in at
That's
some
going to
point.
come in a little later. Yes, we do. Thank you for the question, Kelsey.
Because I think we'll end up having to divide the surface area.
And the houses in them.
Right, because he doesn't technically need to cover. Anyways, it'll work in there somewhere.
Okay, surface area is 4 pi r squared, and that's of a sphere.
Right.
Obviously, the Earth is not.
It's close enough.
It's close enough in our world.
4 pi r squared, and this is going to be equal to again this velocity, right? Vs
Yes.
times this t total. Okay. right?
Right, because this is the area that he has to cover. Boop, 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 boop. That's going to equal the how fast he's going times the time. Yeah, I agree.
So, I mean, I guess we could solve this really easy.
Yeah.
Because we know our time and we know this.
That was a huge breakthrough. That was wonderful.
But that's like the ultimate simplification there. But this is good. This is a good equation to have.
That was if we can't solve it with these other, we can fall back to this.
Yeah.
And we'll say solved, you know? Mathematical, all of these. Right? It will be wonderful.
Should we start with this to get an approximation?
Sure. So I think we need the radius again, right?
Right, which was
6,378 kilometers. So add 3 zeros to get meters. And we need to square that.
Oh yeah, we gotta square that. We gotta times that by 4 and times that by pi, and then we're gonna divide that by 32 times 60 times 60.
Let's start doing this.
Oh boy, dude.
Here, should I cheat and just look up surface area of Earth?
You want?
Nah, I'll just do a calculator. Okay. What are these for?
That's to get it in. So we're at 32 hours.
Oh, you want
In
in
seconds.
Okay,
Yeah.
gotcha. Boop, 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 boop. Boop, boop, boop. Squared.
Big number, dude. I know. I think we're gonna be pushing some physics limitations at this point, dude. I mean, this is a pretty big number, though, too. That's gonna come out pretty big. We're gonna be breaking some rules of physics here. Well, let's find out. I don't think so. I think we're gonna be fine.
Okay. This is equal to 4, 4, 3, 7, 3, 7, 7, 8, 8, 6. So,
How many places is that?
One. It is. Okay, this is 4 billion. 4.4 billion, yeah.
0.4 times 10 to the 9?
Yeah.
Jaden, do you know the problem with that?
Yeah, that's faster than the speed of light, Kip.
Yeah.
And that is... Okay, so, kids out there, anyone watching,
We're not done yet.
Santa is magic. That's what we learned tonight, dude. Okay.
Because for anyone that's curious, the speed of light is 3 times 10 to the 8.
Yeah, and it is, as far as we know, today it is physically impossible for anything with mass to travel the speed of light or faster.
Yeah.
Alright. So that is why we were laughing and we're having a great time and this is just, that's why Santa's magic.
Yep. He's
Okay.
magic. He's full of magic. Anyways, for those, if you want to talk a little more about relativity, right? Anything that starts going over the speed of light actually starts gaining mass and can't really pass that speed.
Yeah.
So it's this weird thing that happens. But
You either you'll run into some complex numbers, or if you're just talking about in the domain of real numbers, it's just impossible. You'll divide by 0, and that is a no bueno situation.
no bueno.
Okay, Kip, where do we want to go from here?
Well, I mean, this is again if he has to cover every
inch.
inch of this Earth, which we know is not the case.
Okay, so how about we do this, right? We know our Earth is about, what, 70% water?
Okay.
Right? So let's take out
70%.
of the surface area.
Okay, we can do that.
So
we're going to divide by 70. Right? Or
times by 0.7.
No, times by 0.3. Because we're taking out 70%.
Oh, yeah. Okay.
Isn't that the same as dividing by... Whatever. We'll do times...
Sometimes I get confused.
Me too.
When okay, so if I times it by 7.7, that
gives
okay,
you
yeah.
70%.
So times by 0.3. Okay, let's do another calculation, shall we?
Jaden, I can help you with this calculation real quick. It's just going to change this by an order of magnitude, essentially. I mean, there's going to be something in here, right? But
yeah.
I mean, it might be close. You could do it. Let's do it. It's going to be close.
Okay. Yeah. Let's do it.
I think it's going to be
Okay.
less.
Let's do this. Doop, doop, doop. Do you like my sound effects?
Yeah. Beep beep bop.
Boop,
Boop
boop,
boop
boop,
boop boop
beep.
boop.
What if what if calculators were just making
Beep,
all
beep.
this noise? Ooh. I'm still working.
Okay.
Beep, 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 beep. Okay, Kip.
Yeah.
This is 1.3 billion.
Still a billion?
Yep.
How? We dropped a whole order of magnitude.
Because it was in the like fours.
I know, but we have a point. I guess, yeah, it's point. Okay.
Yeah. If it would have been
Yeah, if it was a
Oh.
1. Okay. Yeah, you're right. Alright, so
we're still stuck.
Okay. Abby Normal? What?
We have another donation. The Venmo name is Abby Normal. It was $31. That is huge. Thank you so much.
Thank you.
Kip,
We have to sing.
we have to sing another Christmas carol. We're really
Uh,
talented. We should probably be singers.
Yeah, we should start our own channel after this for just singing.
Agreed. Okay.
Let us know in the comments if that's something you're into.
How about Rudolph the Red-Nosed Reindeer this
Okay,
time?
that's pretty good.
You should start us because I'm so bad.
Alright, ready? Here we go.
Rudolph the red-nosed reindeer,
reindeer,
woo!
had a very
Shiny nose like a
light
light bulb. And if you ever saw him,
you would even say it glows.
like a
Glow stick?
glow stick. What's
All
up
of the other
reindeer?
reindeer used to
You
laugh and call him names like Jaden.
Like a jerk face. And then one foggy Christmas Eve, Santa came to say, Rudolph, with your nose so bright, won't you guide my sleigh tonight?
And then how the reindeer
Loved
loved him,
and
as they shouted out with glee.
Woohoo!
They,
That's a good way to end.
yeah, okay, yippee.
I don't know, it's a celebration. Woohoo! Okay.
Okay.
So, Kip, let's
Wait.
just make a
Whoa!
note. We are at $96 total.
We
So-
are only $4 away now from our goal, guys.
$4
$4 away. Let's shatter it. Let's.
Yeah, give us another Christmas carol to sing. I don't know.
Yeah.
We're having a good time. Thank you for your donations. It has been wonderful.
For all of you that don't know, by the way, the food bank.
Huh?
We have a comment from Shaylee or us say we didn't actually know.
Shaylee, obviously we did. We sang it.
Yeah, we did.
Right?
We sang it great.
Okay.
Okay. By the way, guys, the Utah Food Bank, from what I read, said that it's something like for every dollar you donate, it equates to about $8.6 of food.
Oh,
So,
no way.
by the time we get to $100 here, we will have helped essentially raise $860 worth of food.
Okay.
So this is awesome, guys.
That
Thank
is
you so
super
much.
amazing. Yeah, thank you for all your donations, everyone. This has been wonderful. Yeah, we just can't say thank you enough.
Yeah.
All right, back to
We got another $10 from Brad.
another donation, $10 from Brad. Thank you so much.
So we're up to 106 now.
We have reached our goal. That is math magical. What do you think?
It's totally math magic.
Yeah.
Jaden, I think you should strip. Let us know.
No. Kim, come
What?
on, man. We're doing math. I don't want to get cold.
Oh, sorry.
Okay. What else were we doing? So this is still
Too fast.
too fast.
Okay,
'Kay.
but
We took off 70% of the Earth because of water. Now, what do you think? Take off like the poles,
yeah,
some desert regions. This is all going to be estimations, right?
yeah. So let's take off the poles, okay, and let's. I mean, what do we want to?
We need a.
Oh, sorry, we're getting told we need to fill out the bar here.
Woo! Okay. Yeah, we
can take out some poles, and then what I'm thinking from there, we may need to do some population density kind of stuff to
Right.
kind of spread it out a little more.
so
Because
they
we
take
know,
off a lot more of the surface area, right? Because he's not going to be going over the Sahara Desert,
right,
dropping presents down all those chimneys,
right.
right? That just people don't live there.
They might. You don't know, dude.
Well, I'm sure some people do. Sorry, some people do live there. Kid, they want presents too.
Yeah, they do. But you're like, no, they don't get them.
I changed my mind. Okay. So how do we want to go about this? Right now, it's too fast. And Kip, even if we take off, like 80%, 90%,
Should we do some-
95%,
no, let's
I think it's still gonna be faster than the speed of light. Just
Let's-
thinking about it.
Yeah, I agree with you. But let's think about something here, Jaden.
Okay.
Let's go from the point of how magical is Santa. All right, we're gonna stay with that. That he's obviously magical.
Yeah.
We know that.
He's
But
Santa.
we could calculate if we go back to that equation before, how fast he would be traveling just to go up and down, or just up one chunk,
Okay.
and see how little of the Earth he would actually have to travel. Ooh, I just came up with a really good thing that we can Google.
What is it? I'll Google
Let's Google and see what percentage of the Earth is populated.
it. Ah,
That might be a helpful thing.
yeah.
If that, I don't know exactly how that works out. Maybe Shaylee knows. I know that she. Anyways, yeah, we'll find out. Guys, we reached our goal. That's big news, Jaden. Big news.
So just a rough estimate from curiousmeerkat.co.uk. It says about 10% of the Earth is inhabited by humans.
That's not gonna help our cause much.
No. So that'll be timesing it by 0.1.
Which is gonna drop it to, like I said, it's gonna be 4.4
0.4
times 10 to the 8. We're
So-
close.
That looks like a negative sign.
We're close.
So we we're getting closer.
Getting closer.
Maybe.
Let's see if we can get
Maybe
Santa
that's,
into physics.
Yeah. Maybe he has some physics that we don't even know about yet.
Yeah.
Maybe. I don't know.
I'm having a thought.
Okay.
We're assuming right now that that's if he's staying directly above the Earth's surface. All right. Okay. If he's able
to what? Go inside the Earth?
He could cut through. No, I'm thinking more of if he was to projectile launch his presence.
Yes.
He could go up above the Earth.
Okay.
And launch a whole bunch out.
So he just scatters presents into the chimneys.
Right.
So then he wouldn't have to travel at all, right?
Exactly. He could just stay at the North Pole here.
Okay. I like where you're going. Okay. So
I mean, I know technically Santa Claus is supposed to go down every chimney. I'm aware of that.
Right.
And that's possible because Santa is magic, like we already discussed.
He is.
He's super magic, okay? But also, Santa came about before the Earth had 0.1% of the Earth covered.
Ooh, so you're...
So what I'm saying is back when Santa Claus, first was coming about, he may have very easily been able to do this. Because our population has boomed like crazy. It's an exponential growth function. We talked about those a lot.
So what you're saying is his technology is advancing like ours with our population. So he has other ways to deliver presents now.
Right.
Okay, I like where you're going.
Because he doesn't want to make Einstein feel bad, right? He doesn't want to hurt Einstein's feelings.
No, he doesn't.
I mean, he could throw some wormholes in there maybe and pop in and out.
Maybe. How much extra time would he need to get that? A lot.
I mean, if we just threw one more zero in here somewhere, then...
Yeah, 320 hours?
Yeah.
No. This is in meters per second. Let me...
I mean, it is past 8 o'clock, Jaden. If we want to stop it, we can. Or we can keep going.
That's true.
And we got a lot of time on our clock still, and who knows? I mean, our viewer count is dropping.
Yeah.
So,
should we ask in the chat?
Let's ask. Do you guys want us to keep going?
So right now we're kind of just theorizing, right? We already found out from a Rust estimation that he has to travel a lot faster than the speed of light, and that is not physically possible with anything that has mass. So we concluded that Santa is magic and he can travel that fast because he's Santa. So if you want us to continue theorizing about different ways to cut his velocity down, let us know in the chat. Or if you have any questions, let us know. And if not, then we will...
Oh, we do have a question that says, then who eats the cookies?
Oh, if Santa just shoots them off?
He's got a giant vacuum. He shoots them off and then sucks them back up in.
Yeah, that's when he tells the parents to eat them. I don't know.
Okay.
Well, our breakthrough happened right here.
Yeah, it did. That was a good breakthrough.
We didn't even have to say a number of houses he had to visit because he just went all the way around the whole Earth.
I know. I'm trying to figure out though if that would It doesn't matter.
It doesn't matter.
It doesn't, because he's still got to make the
'Cause-
distance.
Yeah, no matter how much of the Earth is populated,
He's still
right,
got to travel. that
even if
distance.
you multiply this by 0.01, that would still just take. Would that work?
It'd be close. I mean,
I mean, we'd get closer and closer, but that's saying there's like less and less population.
well, but the thing is, though, Jane, that I'm saying is, I mean, how we have it set up is the main distance that we want to try to shrink is the vertical distance, right?
Right.
And somewhat this way. But the thing is that he still has to, regardless if there's a house there,
He still has to travel over
He
it.
still has to travel over it, and so that's
the problem.
That's the problem. He can't just magically teleport and miss a section of the Earth.
Right.
He could cut through and go down and then back up.
He just. What is that called when?
But even then, you'd have this triangle effect, and I think that would be the same distance. I think so.
I think we're solved, right?
I think we are solved.
I don't know if there's
Yeah,
any way. I kind of like what we were saying. Unless we gave him more time, maybe with general relativity, with time dilation, maybe he gets more and more time.
But he wouldn't
some-
get last time.
Yeah.
However,
I don't know.
if I don't know. I mean, he may be heavier with all of his presence, and that will affect time dilation as well.
Right.
Because that's a lot of.
We didn't even think about length contraction. Maybe he's just so long. Okay.
Well,
Anyway,
this is solved for this year. Maybe we'll revisit this problem next year.
Yeah.
And go again. We'll think about it a little more. But I think that
yeah.
we are solved tonight. We made our goal. Thank you guys so much again for your donation.
Please like and subscribe if you haven't already. That just helps a bunch. And yeah, thank you all for your donations. That is just wonderful.
Yeah. And just so you guys know that this channel is all about charity, right? So our goal is to reach out and help those that may be struggling in math or physics that can't normally afford a tutor, because tutors are psycho expensive.
Yes.
And so Jaden and I both have a lot of math and physics knowledge.
Yep.
And so we try to go out and, help those that we can by doing this channel. So if you know anyone that needs help, please let them know.
Yeah, spread the word. Thank you all. Good job, Kip. Thank you for being our main scribe tonight.
Dude, you should
That
have
was
been the main
wonderful.
scribe.
That would have been
handwriting's-
awkward though.
That's true.
Okay. And thank you all again for your donations. This has been a huge $106, Kip. Like you said, that's